So in the last class, we have seen that time period t can be written as t equals to twice pi by omega naught, and frequency can be written as 1 over t. So here, frequency can be written as twice pi times omega naught. So this term omega naught is called angular frequency, which for a mass spring system can be written as k by m root over k by m. Now the question is that why the term angular has been used here. The motion of a spring is linear, the linear motion. So how why the term angular has been used here? Actually, yes, anyone wants to answer?
Yeah, because it's periodic and it's মানে এটা হচ্ছে একটা সার্কেলকে কেন্দ্র করে মোশনটা হচ্ছে, দিস ইজ ওয়াই।
So স্প্রিং এর মোশনে সার্কেল আসলো কই থেকে?
সরি স্যার, একটু পিরিয়ডিক মোশনের কথা বলতেছিলাম আর কি।
আচ্ছা, সো তোমার অ্যান্সারটা is not a bad answer, actually is quite close to correct answer, but the point is that কারেক্ট অ্যান্সারটা আসলে পুরোপুরি আসে নাই। হ্যাঁ, অভিনন্দন, বলো।
স্যার বিকজ ওর অ্যান্সারের থেকে আমি একটু এক্সপ্লেন করে বলছি। বিকজ ইন আমরা ওই মাস লোডেড স্প্রিং এর জন্য আমরা যে ইকুয়েশন ফর দ্যাট মোশন ওখানে আমরা সাইন পাচ্ছিলাম, সাইন অর
রাইট,
কোসাইন ফাংশনস,
রাইট।
এন্ড ওইগুলোতে আমাদের লাইক অ্যাঙ্গেলের যে ফ্রিকোয়েন্সি থাকে, আফটার দ্যাট ফ্রিকোয়েন্সি দ্য অ্যাঙ্গেল রিপিটস ইটসেলফ দ্য পিরিয়ড।
Okay, so a bit more close, but the point is that actually we will learn the answer hopefully in the next class. So why the term angular has been used here. So far, let's just focus on the mathematical form. The angular frequency is given by omega naught, which is root over k by m, and it is related to time period and frequency by this formula. Now we have seen that this can be one of the solution for simple harmonic oscillation. Now at t equals to 0, sorry, it was a sine omega t plus d, I think. So at t equals to 0, x becomes a sine d, right? So let me check. Let me check what was the symbols. Did you remember what was the symbol? What were the symbols for amplitude and uh, phase in my lectures? Let me check. Okay, so in my solution, I used C and D, and I already explained that C denotes amplitude, and we will use basically A instead of C. So we will use this formula A sine omega t plus d. Now A sine omega t plus d x equals to, this will be the solution for simple harmonic motion. Now at t equals to 0, x becomes a sine d. Okay, so since a is a constant, x depends on the value of an angle d at t equals to 0. This angle, this value of x is the initial position of the oscillating object. So the initial position of an oscillating object depends on an angle. This angle is called phase constant or initial phase angle or phase lag. Now look, when this d equals to 0, then x equals to 0. Okay, the initial position, so initial position should be written by x naught, should be denoted by, if d equals to pi by 2, x naught equals to a. Okay, so for this case the oscillation will be start from 0 and will be like this, and for this case the oscillation will start from here and will be like this. Okay, so the symbol for phase constant or initial phase angle or phase lag is actually phi. This is the symbol which is used in almost in every text, and we will also use that. So the solution is sine omega t plus phi. Now, so it is our solution, right? X equals to a sine omega t plus phi. So what will be x dot? X dot will be plus omega a cosine omega t plus phi, right? And what will be x double dot? Minus omega square a sine omega t plus phi. Now if you plot x equals to a sine omega t plus phi, let's say phi equals to 0. Okay, so for phi equals to 0, this is x versus t graph. Now what should be the form of v versus t or x dot? This should start from here, and this height should be equal to omega a. Okay, and the acceleration should be like this. Okay, so is my drawing is correct? The acceleration গ্রাফটা ঠিক আছে না? Minus omega square a, right? So A equals to minus omega square A sine omega t. So when t equals to 0, it should be 0. When t equals to omega t
স্যার
equals,
উল্টা হওয়ার কথা না, upside down.
there is a minus sign, right?
Yes.
So if there is a minus sign, omega t equals to pi, then x equals to what? If omega t equals to pi by 2, sorry, omega t equals to pi by 2, then this is omega square A, right? And this is pi by 2, this is pi, where is 0? This is 3 pi by 2, where? So look, the acceleration and the displacement both are in same phase, but there is a the actually the what should I say, the phase angle is same. Okay, the argument of sine function is same, but there is a minus sign uh, before the expression of, before this term in the expression of acceleration. So this minus sign means that the displacement is proportional to the acceleration, is proportional to the displacement but opposite. And what is the phase difference between the velocity graph and the displacement graph? Phase difference between velocity and displacement of an oscillating particle?
Sir, pi.
Sir,
No,
pi by 2.
Pi by 2, right? Pi by k. So our discussion about interpretation of the solution of simple harmonic oscillation is done. Now, is there any question?
Sir, I had a question from previous lecture. Should I ask it at the end of this class?
Yes, end of the class. Okay, so now our new topic will start, and the new topic is angular simple harmonic oscillator. So it is not in box, I think. Angular simple harmonic oscillator. So what is that? So let's say we have a disk here, and a disk is connected to a support by a suspension wire. So this is the support which is fixed, so we will call it fixed end. This is the suspension wire. Now so this is actually an angular version of simple harmonic oscillator. Now in the previous case, that is in a spring mass system, there was a spring and a block. Here we have a suspension wire and a disc. The element of springiness or elasticity is associated with the twisting of a suspension wire rather than the extension and compression of a spring here. the element of springiness or elasticity is associated with the twisting of a suspension wire rather than the extension and compression of a spring. This setup is also called torsion pendulum. Torsion pendulum. So with torsion referring to twisting. So what we want to do here now, if we rotate this disc in figure 1 by some small angular displacement theta, let's say this line is our reference line, and when the line is here, it is at the disc is at theta equals to 0 position. So this is theta equals to 0 position. Now if we rotate the disc in figure 1 by some small angular displacement theta from its rest position to the right or to the left, the disc will start to oscillate. Okay, it will first come back to its initial position, then goes back to left. Let's say the disc is rotated an angle theta towards right, and then if you release it, it will come back to its center by or equilibrium position, and then it will go to left, then again it come back to the initial position, and again it go back to the right. Now if you neglect all the resistance effect, then the oscillation will continue. So this is angular simple harmonic oscillator. So the since when you take it to some position and then you release it, the disc makes some rotation towards the equilibrium position, right? So whenever a object rotates, there is a torque, and as like spring mass system, the torque here is called restoring torque. So similar to the spring mass system, this torque is proportional to the angular displacement and is opposite to the angular displacement, and here the constant K is called torsion constant. So it depends on K depends on length, diameter, and material of the suspension wire. Now this is basically the angular form of Hooke's law. Okay, so in case of spring mass system, we had F, X and spring constant K. Here we have tau, theta and torsion constant K. So for spring mass system, T equals to twice pi m by K. Here time period should be twice pi what? Can you tell me? What it should be? Moment of inertia I divided by torsion constant K. So angular frequency here, root over K by M. Here angular frequency torsion constant by moment of inertia. Okay. And the frequency is 1 over twice pi K by M, and here the frequency 1 over twice pi torsion constant kappa divided by moment of inertia I. So this is basically a Greek letter kappa. I think all of you are familiar with the letter. So this is angular simple harmonic oscillator. Now, any question about this? So no question. Okay, now let me ask you one question. Have you understood the word twisting here? What gets twisted here?
Sir, continuous displacement, is it?
Not really. What component of the device angular simple harmonic oscillator gets twisted?
The disc.
The disc. And any more answer?
So it's not the disk, it's the cable or the string that's holding the disk.
Yes, the wire. Good. So it's actually a very common scenario. I think all of you have seen this. In বাংলায় হচ্ছে যেটা বলে হচ্ছে পেঁচায় যাওয়া। হ্যাঁ, তো আমরা যখন ওইখানে রোটেট করাই, উপরের তারটা হচ্ছে পেঁচানো শুরু করে। সো আবার যখন রিলিজ করে দেই, প্যাচটা খোলা শুরু করে। তো এইটাই হচ্ছে এখানে টুইস্টিং। ওকে, so our next topic, simple pendulum. So what is simple pendulum? Simple pendulum is basically a particle of mass m suspended from one end of an unstretchable massless string. This is the unstretchable massless string of length L. Okay, so that is fixed at other end. So the string is fixed by this. The particle of mass m is called the bob of the pendulum. The bob is free to swing back and forth in the plane of the board to the left and right of a vertical plane to the pendulum pivot's point. Okay, so here is the vertical plane and pendulum pivot point. Here is the pivot point. Okay, so this is our simple pendulum. Okay, Now write of a vertical line. Here is, this is a vertical line, sorry. So now we want to see at uh, at which condition its motion becomes a simple harmonic oscillation. So basically, after completing the discussion about interpretation of solution of simple harmonic oscillation, I am showing some examples of simple harmonic oscillation in different systems. So we have seen angular simple harmonic oscillator. Now we will see another system which whose motion is simple harmonic motion at some certain condition. Okay, so here the force acting on the bob, what are the forces? One force is the weight force due to the gravity, and another is the tension force. Now let's say this string makes an angle theta with the vertical line, then this angle is also theta, and this component is Fg cos theta. So since there is no motion along this line, so T equals to Fg cos theta. Okay. Now Fg equals to what? Fg equals to mg, the mass of the bob, times g. So T equals to mg cos theta. Now the sine component of the gravitational force Fg sine theta, what is its role? Due to this force, the bob comes to its equilibrium position and then goes to left, and then again at this point the force, the sine component acts towards again equilibrium position. So due to this force, the bob starts to oscillate. Okay, so the Fg, the tangential component, this is the tangential component or sine component. The sine component of Fg gives a restoring torque about the pendulum pivot point. Okay, so Fg sine theta gives a torque, that is, a torque is acting on this bob since it is rotating about this pivot point, and the torque has been created due to Fg sine theta. Now we want to know the magnitude of the torque. So torque equals to, here you know the magnitude of a torque is R Fg sine theta. Now here wait a second, sorry, this is the force. Okay, so what we want to do, let me tell you one thing, that is, this is the force here, Fg sine theta, this is the total force, and this is R, the distance, this length is R, which is the distance from the pivot point to the bob. So magnitude of tau will be R cross Fg sine theta, sorry, magnitude of R times magnitude of Fg sine theta times sine phi, the angle between R and the force. So this is the force and this is R, the angle is 90 degrees, so sine phi is sine 90, so it will be minus R Fg sine theta. Now R, the distance, equals to the length of the string, which is L, so this is L Fg sine theta. Now why the minus sign is here? the minus sign indicates that the indicates that
So the torque is applying opposite direction, right?
right, torque acts to reduce theta, in other words. Okay.
Sir, I have a question, sir. What if the
Yes.
pendulum is oscillated in zero gravity?
So zero gravity.
Like in space or something like that?
Okay, nice question. So what will be then? So if there is zero gravity, so there fz equals to 0, right? Then what it will be? So the bob will go towards along t. Okay, the bob will move towards along this line, and then it will hit this sand, and then it will follow the physics. So far এটাই মাথায়
তার মানে
আসতেছে
হচ্ছে
উত্তর।
স্যার এটা কোনো মানে অসিলেশন বা সিম্পল হারমোনিক অসিলেশনকে ফলো করবে না, রাইট?
না, ফলো করবে না।
ওকে স্যার।
Sir, why would it be moving towards the plane, or why would it moving along T? Because it should be T only acts because as a reaction force, right? Because if it's just there, like the object is just there, it should be free floating.
Wait a second, let's consider this, that if we have a stand in a spaceship, okay, so in a ceiling of a spaceship, and a bob is attached to an string, then what will happen? Let's say এরকম একটা স্পেসশিপ
It
বানাই
will
আমি।
just stay there, right? Just floating and attached to the string, attached to the ceiling.
মানে ধরো হচ্ছে এটা এরকম ভাবে আছে, ববটা কেন ফ্লোট করবে? মানে এটা এটা এদিকে যাবে না?
There is no force acting on it. String তো just ওটাকে ধরে রাখছে. But I think, as far as I knew, tension only works as a reaction force. Only when there's something acting alongside it.
আচ্ছা, এটা এটা একটু আমি দেখে জানাবো, হ্যাঁ, নেক্সট ক্লাসে অ্যান্সার ভাবতে হবে। So where, okay, minus indicates that torque acts to reduce theta. Now from equation 1 we can write let tau equals to I alpha and fg equals to mg. Now if you use equation 2 and 3 in equation 1, you get I alpha equals to minus mg L sine theta. Now if theta is very small, then sine theta is approximately equal to theta. In that case, I theta is approximately equal to mg L theta. So sorry, I alpha. Now from here we can write alpha equals to minus of mg L by I theta. So this is analogous to the equation of simple harmonic motion equation, and that we have seen in case of spring mass system. In that case it was minus k by m x. Here instead of a we have angular acceleration alpha, instead of x we have angular displacement theta. So what is our, and instead of mass m we have moment of inertia I, and spring constant here, the analogous term to spring constant is K equals to mgl. Okay, so now what will be the value of angular frequency omega naught? Omega naught equals to mgl by I, root over mgl by I. Then time period t equals to twice pi times I by mgl, root over I by mgl, and f equals to 1 over what it will be, twice pi mgl by I. Okay, so this is the equation for frequency, time period, and omega naught for simple pendulum. Remember that motion of a simple pendulum, that is, if you displaced, the motion of a simple pendulum swinging through small angles is simple harmonic motion. Let me write this line, this is important.
Sir, is sine theta approximately equal to theta for all cases?
No,
তাহলে
let me write this line: the motion of a simple pendulum swinging through small angles is simple harmonic motion. Swinging through small angle, if the simple pendulum swings through some angle, some small angle, then the motion is simple harmonic motion. Otherwise it will be a oscillatory motion, okay, not simple harmonic motion. And if the angle is small, then you can write it sine theta is approximately equal to theta. Okay, is there any question, any more question? So no question. Then the physical pendulum. So the difference between physical pendulum and simple pendulum is that physical pendulum can have a complicated distribution of mass. Okay, so let me check. This is okay. So here we have, this is our actually pendulum. This is the pendulum. So this is our pivot point. Now let's say this is the center of the mass of the system here. So actually we can now consider the center of the mass as the bob of this pendulum. So let's say this is at a distance h from the pivot point. So in that case, what will be the uh, formula for time period and angular frequency and frequency? The angular frequency will be, it was here mgl by I. In this case it will be mgh by I, root over mgh by I. Time period will be twice pi I by mgh, and frequency will be 1 over twice pi mgh by I. Okay, so this is the equations of frequency, time period and angular frequency for physical pendulum. Okay, so have you understood the difference between physical pendulum and simple pendulum? Is there any question? Hello.
So understood, sir, the
Okay,
difference.
so here I depends on the shape of the physical pendulum. And is proportional to what? Will it be proportional to the total mass of the physical pendulum? Hello. Yes. And a physical pendulum will not swing when? Will not swing if it pivots at center of mass. In that case, h equals to 0. Then time period becomes infinite, which means such a pendulum will never complete one swing. Okay?
Sir, one question.
Yes.
Sir, in this example, we are like kind of considering like instead of the small, the pendulum, the physical pendulum is actually hanging from a ceiling.
Right.
Would it be possible if the let's say it's just a cone shaped object and it's just on the ground, not on the ceiling, and then it's wobbling or like moving in a periodic motion?
Cone-shaped object on
So
the
it's like other way around. The gravity is downwards, but it's left to right, but
okay.
it's not. The pivoting is on the ground, not on the ceiling, on the floor.
I think it's possible.
Would it change anything in our calculation?
But will it change anything? I have to check. But I think it's possible. We can
It
make
is
it
definitely possible. If it's a periodic motion, it's definitely possible
possible.
for it to.
Okay. But I have to check what changes will we have to bring in our calculation for that. So দেখি যে আমি কোনো একটা কনক্রিট এক্সাম্পল পাই কিনা এরকম, তাহলে আমরা এটা নিয়ে ডিসকাস করতে পারি। ওকে,
Sure.
let me give, okay, wait for 1 minute, coming back. So okay, am I audible?
Yes, sir.
Yes, sir.
Fine. So they are function of time. Now let's say we want to measure the voltage across the capacitor, and we want to measure the voltage across the inductor. So what is the voltage between the plates of the capacitor? Voltage is given by Q by C, and here the voltage is also a function of time, because charge is also the function of time. Okay. And what is the voltage across an inductor? It is given by, let's say this is Vc, VL equals to L di by dt, where I is the current to the inductor. Now we can write for this LC circuit Vc plus VL equals to 0 using which law? Using which law? এটা তো তোমরা সবাই জানো, বলতেছো না কেন? কোন ল ইউজ করে লেখা যায় Vc plus VL equals to 0 একটা সার্কিটের জন্য? সার্কিটটা একটা ক্লোজড লুপ।
Sir, Kirchhoff's law.
Sir, KVL.
ইয়েস,
KVL.
রাইট,
Sir.
এটাই তো বললাম যে তোমরা সবাই জানো KVL. So okay, then we can write Vc equals to Q by C and VL equals to L di by dt equals to 0. From here we can write Q by C plus L dq by dt, then can write Q by C L d square Q by dt square equals to 0 equals to 0. And here finally we can write d square Q by dt square 1 by LC times Q equals to 0. So this is the equation of simple harmonic motion for LC circuit. If you replace Q by X, 1 over LC by K by M, then you get the simple harmonic equation of motion for simple harmonic motion in spring mass system. Okay. So this equation tells us that the amount of charge varies with time, and the variation is analogous to simple harmonic motion. Now what will be the solution of this equation? Solution will be Q naught time sine omega t plus phi, and at t equals to 0 and if phi equals to 0, then Q equals to Q naught. Okay. Now here 1 by LC is the angular frequency of this LC circuit, which is also called the resonating frequency. So we can write omega naught equals to 1 by LC whole to the power half. From here we can write T equals to twice pi by omega naught, so twice pi by 1 over LC to the power half, sorry, twice pi by twice pi times root over LC. And what is the frequency here? 1 over twice pi root over. Now tell me one thing. If there is no resistance in the circuit, that is, it is an ideal circuit, then will this oscillation continue infinitely? That is, up to t equals to infinite time t, মানে এটা কি চলতেই থাকবে কিনা যদি কোনো রেজিস্ট্যান্স না থাকে, যেমন এই সার্কিট?
হ্যাঁ চলতেই থাকার কথা স্যার।
রাইট, it will continue indefinite, but in real life circuits এখানে রেজিস্ট্যান্স ড্যাম্পিং ফ্যাক্টর হিসেবে কাজ করে। So these are the examples that are for simple harmonic oscillation. We have seen some mechanical systems. One is simple pendulum, one is physical pendulum, one is spring mass system, and we have seen a non-mechanical system, which is LC circuit. Now in the next class we will talk about energy of the oscillator in simple harmonic motion, number 1, and number 2, the relation between simple harmonic motion and circular motion. Now